Okay, let us start the class now. We had a general discussion on basics of transistor yesterday. Today I am starting the actual concepts of this particular module. You can see this picture here on the screen. These notes I have already shared in the Google class. To this BJT, one collector resistance is given and one base resistance is given. To the base, one power supply is given, and to the collector, one power supply is given. In general, we have a terminology. Wherever a collector is connected with the resistor, we call it as RC, and for the base, we call it as RB. For the power supply, we give this VBB just to differentiate it from VB, because VB denotes voltage at the base with respect to ground. But here, this is VBB is the power supply given to base. So the voltage exactly at the base is different from the voltage given at the other side of this RB. That is why we use the terminology VBB. Similarly, for collector voltage, we give the VCC just to differentiate it from the voltage at the collector, which is actually VC. We also call, in this case, we call it as VCE because it is between collector and emitter. But as emitter is grounded, we can simply call this as VC as well. So generally, always power supply to the collector is called as VCC. Power supply to the base is called as VBB. If at all there is any power supply to the emitter, that is called as VEE. This is the general terminology when we use power supplies or for voltages. Now look at this particular circuitry. To the base we connected one resistor. I have purposely put a potentiometer here. We have connected a power supply. And why this resistance is required to the base? Because any transistor base to emitter junction is a PN junction and it can handle only 0.7 volts. We cannot give more than 0.7 volts to a silicon transistor. The two, we cannot exactly say that it is 0.7. It can be 0.69 also, it can be 0.71 also, it can be 0.68 also. Sometimes it can be 0.65 also, it can be 0.75 also, it can be 0.8 also. Why such a difference is there? The reason is, just like we cannot have two human beings who are identical in the complete earth. You cannot find a person just like me all over earth because I am uniquely manufactured by nature. Similarly, you cannot find a person who is identical to yourself. You are also uniquely manufactured by nature. We cannot find a person who is physically identical. Even if a person is there in twins who is physically identical, there can be minute differences between the twins also. And you cannot find a person who is having an appearance like you or a voice like you also. Each person's voice is unique. Each person's voice is different. Because we are all manufactured by nature. In other words, we are all manufactured by God Himself, who is the Lord of nature. Same way, it is not possible to manufacture two transistors having the same beta. That is why yesterday I had told transistor is the eighth wonder of the world. I keep on repeating this sentence as many number of times as possible because it is not possible to manufacture a transistor having the same beta. Reason is we only dope the semiconductor silicon using the dopants, either boron or arsenic or phosphorus. Now when we use the dopants, we are not controlling the number of atoms which go into the silicon surface. We are only passing the boron gas or we are going to pass the arsenic gas on the surface of silicon and or phosphorus vapor also. If it is for N-type or P-type, respectively, we are choosing the dopants, but we don't have a control over the number of molecules or number of atoms which are going to be combined along with the silicon atoms. We are not doing any atomic level doping there. We are only doing the surface level doping with optimum temperature and optimum pressure. So when we don't have control over the number of atoms as such, we do not have a control over the number of molecules which are going down into the silicon. So in that case, as transistor is so small device, it is an invisible device to the naked eye, as I told yesterday. As it is not possible to control the number of atoms, or for that matter, we cannot control the number of electrons as such, which are being dispelled out of the orbits of silicon. So in such a case, we cannot manufacture two transistors having same beta. Some transistor may be having a beta of 70, it may be 80, it may be 90, it may be 100, it may be 60. That is why manufacturers, they don't give a single number to the value of beta. They give a range of numbers, in general between 60 to 80, where it can vary between 60 to 80. So in such a case, as it is not possible to manufacture two transistors which are identical, we cannot actually define that the VBE is always 0.7. It can be 0.71, it can be 0.69, it can vary between 0.65 to 0.75 also. In that way, we cannot always say it is 0.7, but in general we say silicon's base to emitter voltage is 0.7 volts and for germanium it is 0.3 volts. Now if this is 0.7, we connect a supply voltage, we cannot actually have a supply voltage of 0.7 because here it is varying. Base to emitter potential, when it is varying, but we are going to have a fixed voltage. So the solution what we find is, we connect a supply voltage which is larger than 0.7. Maybe it is 1 volt, 2 volt, 3 volt, maybe 5 volt, maybe 10 volt also. This VBB has to be greater than 0.7 for the transistor to switch on. It cannot be less than 0.7, but we cannot fix it at 0.7 because VBE is a dynamic value which is variable value in millivolts. Always the base to emitter voltage is in millivolts. For that reason, we connect a standard supply voltage, maybe 2 volts, maybe 3 volts, and we connect a resistance here so that transistor will, when it turns on, it will have a base to emitter junction potential which is the characteristic value of the transistor itself. The remaining voltage will be across this RB. So for this purpose, RB is required. Otherwise, we can always connect a 0.7 volt supply voltage to transistor itself, no. But as I told you all the reasons, it is not possible to have a variable supply voltage for a variable characteristics of the transistor. For that purpose, we connect a standard supply voltage, we connect a resistor here. So I am telling you why this resistance is necessary. This resistance is very much necessary so as to standardize the supply voltage. We cannot standardize the beta of the transistor. It is not possible as such. Now if RB is required for this purpose, why RC is required? RC is required because we already know that transistor is a switch. When transistor is a switch, if this transistor is switching on, let us say this is like a push button. Yesterday I gave an analogy of the keys which are available in the keyboard of a laptop or a computer. You can press it hard, you need not press it, or you can press it half also. You can keep this switch half on, half off also. That is the specialty of the transistor. Transistor can have 3 regions of operation. One is completely off, completely on, half on also. That is the reason yesterday I gave you the analogy of Tirupati Laddu. So if it is fully on, it is called as saturation region. If it is fully off, it is called as cutoff region. If it is half on, then it is called as active region. Now, let us say this transistor is completely on. Imagine the transistor is completely on. From collector to emitter, it is completely on. Then the switch is closed. If the switch is closed, I have a power supply at the output as well. Now, power supply will get short circuited to ground if this RC is not there. So it is necessary that one more resistance is required at the collector also. When the switch is turned on, power supply should not be short circuited. Otherwise, there is a danger. If power supply gets short circuited, transistor will burn out. We want to use a transistor as a switch. That is the reason we have RB and RC. Now look at this circuit diagram. Let us assume that VBB, I will start from 0 and I will gradually keep on increasing. Imagine that way. That is why I have shown you a variable resistor here. So let us say this variable resistor, initially let it be maximum, I will keep on reducing to a minimum value. Imagine that way. Now in that case, you can see the right side curve here. Initially, the voltage at the base will be 0. Look at this. Initially, the voltage at the base will be 0. Now gradually when I keep on varying the value of RB to the lower side, here at the base, voltage will keep on rising. When the voltage will keep on rising, let us see what happens here. When the voltage rises up to 0.5, imagine that way, this is slowly rising. When it is slowly rising, the base current will be slightly increasing because base to emitter junction will be slightly forward biased and the current at the base will be increasing. Now when the current at the base is increasing, let us see what happens at the collector. You can see here, when VB is slowly rising, IB is also slowly rising. This we call it as a non-linear curve. Non-linear curve. BJT or the bipolar junction transistor is the active device. You may remember which are the passive devices, which are the active devices. Resistors, capacitors and inductors are called passive devices because they follow Ohm's law. Generally they follow Ohm's law. But diodes and transistors are categorized under active devices because diodes and transistors do not follow Ohm's law. The reason is, resistors, capacitors and inductors, they are made up of single material, where transistors are made up of multiple materials, either P and N or N and P or P and P or N P N. There are dissimilar materials joined together in case of diode and transistor. Whereas in resistor it is a single material, capacitor it is a single material, inductor it is a single material. That is why they follow Ohm's law. Transistor and diode, they do not follow Ohm's law. The basic reason is they are comprising of dissimilar material combination. So in such a case, their behavior is not as simple as the passive devices. Transistors and diodes behavior is not a linear behavior. It is a non-linear behavior. The reason is, you can see this is not a straight line. If it is a straight line, we can say it is a linear behavior and we can predict its behavior. For a given voltage, this is the given current. For example, for any resistor, you can apply the formula V equals I into R. You can always calculate the amount of current I equals V by R. And you can predict. That is completely mathematical, linear. But here also, it is mathematical, but it is non-linear because with the increase in VBE, IB is increasing in a non-linear fashion. That is when in maths we use the terminology of quadratic equations, or we use e power x. We use this e, or we use the trigonometrical functions to represent such lines. These lines are not linear lines. I cannot use the term y equals mx plus c for this line. I'll have to go for either a differential equation or a quadratic equation. I have to represent this line in a different mathematical form, which is a complicated form. That is the basic difference between linear and non-linear devices, and the behavior itself is non-linear as such. So when the behavior is non-linear, you can see when VB slowly rises, IB also slowly rises, but in a curvature fashion. Now look at the curve which is below. If I keep on raising this voltage, let us say up to 0.5 or let us say up to 0.6, let us imagine that transistor will not turn on because it is a PN junction. Transistor will not turn on. Now gradually when I raise, at one point of time, transistor will completely turn on. Look at this picture. Let us say at 0.7, when VBE reaches 0.7, transistor completely turns on. From collector to emitter, now current flows. Because from emitter to collector, electrons flow. From emitter to collector, electrons are moving in this direction because this supply voltage is attracting the electrons in this direction. So there is a base which is very small. Collector is much larger in area. Emitter is medium sized in area. But emitter is heavily doped. Collector is medium doped. Whereas base is a very small region. Base is very thin. So as soon as this PN junction is forward biased, electrons from the emitter will move towards the base. But base is very small. So let us say 100 electrons are released from the emitter. In the base, let us say there is a vacancy for only 10 electrons. Then the remaining 90 electrons will move towards the collector. That is how emitter to collector, electrons are moving. And current is moving from collector to emitter because we measure current always from positive to negative. Electrons are moving from negative to positive. So that way when this transistor switches on, you can see at the right side, when the voltage at base to emitter is 0.7 volts, let us say transistor is completely on. If this transistor is completely on, collector and emitter, there will be no resistance at all, it will be zero resistance. When there is zero resistance, now switch is completely on. That means all the voltage will be across this RC now. Supply voltage will be from RC because transistor is completely on. But we are taking output at the collector itself. In between collector to emitter, we are taking the output. So, if switch is completely on, you can see at the right side, collector to emitter voltage, ideally we can take it as 0. You can see at the right side, ideally we can take it as 0. Reason is, switch is on. So, now see, let us say until 0.5, switch is off. After 0.7, switch is on. Until the base voltage reaches 0.5 volts, PN junction is not fully forward biased and switch is off. So, you can say transistor is in cutoff region. If the transistor is completely off, what is the voltage here? Voltage is the voltage of the supply voltage itself is coming here, but no current is flowing. I can give an example. Let us say you have an electric switch at home. When the electric switch is off, at the other side voltage is there. It is not going to your electrical appliance. Let us say you want to switch on the fan now. When you want to switch on the fan, fan is off means switch is off. Switch is off means at the switch's other side voltage is there. But through the switch, current is not flowing. Then you can say the switch is in the cutoff region. When you switch it on, across the switch, there will be no voltage because all the voltage is going to the fan now. But across the switch, current is going. Across the switch, there is no resistance at all. That is what is this meaning. If the transistor is off, voltage at the collector is VCC itself. Just like your electrical switch, if the switch is off, the other side of the switch, whatever is the 220 volt supply, that will be there. Once you switch it on, then all the voltage goes through the switch and voltage goes to the fan. So that is how when the switch is turned on, across the switch voltage is 0. When the switch is off, across the switch voltage is whatever is the supply voltage. I am seeing in the chat box, can you share the recording of the meeting in the Google class? Yes, I will be sharing a recording in the Google class, don't worry. Yeah, I know you are not able to hear due to voice breakage. That is because of this Wi-Fi connection and network connection. We will have to bear with this. That is why I will be recording this and I will be sharing the recording in the Google class also. Maybe in future I will create one YouTube channel for this class, and in the YouTube channel also I will be sharing all these recordings. Okay, don't worry. Fine, let me resume my talk. Where was I? Yeah, if the switch is completely off, that means base voltage is below 0.5. Then the supply voltage is appearing across the collector. That you can see as VCC here. VCE, collector to emitter voltage, at that time is VCC itself. Now when the transistor is completely on, let us say base voltage is above 0.7. Now across the transistor there is no voltage at all. Switch is completely on. So across the switch voltage is 0. So this is cutoff region and this is saturation region. Now in between is that non-linearity. As I told you yesterday, transistor is a eighth wonder of the world. I keep repeating this as many number of times as possible because I am fond of this switch. This is having 3 regions of operation. One is off, one is on, one is half on. So in the middle region here, it is half on. You can see this. Transistor was completely off till the base voltage was 0.5. Gradually it started turning on. And when the transistor base voltage is 0.7, it is completely on. In between, transistor is in the process of turning on. So exactly at 0.6, let us imagine between 0.5 to 0.7, exactly at 0.6 what is there? Exactly at 0.6, if the transistor is half on, then what will be the voltage drop across the transistor? If it is fully on, it is 0 volts. If it is fully off, it is VCC. In between, it is half on, it is between 0 to VCC, that means it is exactly at VCC by 2. This is the point which is called as quiescent point. Remember this word? The point where the transistor is half on, it is also half off. That is called as a quiescent point. The meaning of the word quiescent means it is a very sensitive point. Quiescent means quiet as well as sensitive. Both are there. Quiescent, you can say quiet, and quiescent, it is sensitive. It's a combination of quiet and sensitive. Transistor is quiet. It is quietly waiting. It is asking, give me a little more voltage, I'll turn on. Give me a little more voltage, I'll turn on. Or reduce a little more voltage, I'll turn off. That means it is highly sensitive in this region. So remember whatever I told you yesterday. If the transistor is used in the off region and on region, it is used in the digital electronics only for 0 and 1. If it is used in the middle region here, exactly at VCC by 2, I am using it as analog circuit now. We can gradually use it as an amplifier and oscillator in future. So it is highly sensitive at this particular point. That is why we use a term called biasing. Using biasing, we set this voltage exactly to be at VCC by 2 and we give a small input at the base so the transistor will slightly turn on, slightly turn off, slightly turn on, slightly turn off. Then I can use it as an amplifier. So I hope you got this point. This is the region which is called as active region where the transistor is half on. Otherwise it is completely off, completely on. But as the transistor is a non-linear device, we have this ability. If it is a linear device, it cannot be in active region at all. Understand that. If it is, let us say your switch at home is only a single switch without the regulator there for the fan. You will simply switch the fan on, fan will be high speed. You simply switch the fan off, it will low speed. But you have a regulator at home and you can select the speed up to which the fan has to be on. Maybe speed 1, speed 2, speed 3, speed 4, speed 5, that way. If speed is 5, then it is fully on, which means completely all 220 volts is given to the fan. If it is fully off, all the voltage is at the other side of the switch. Now if it is half on, maybe 110 volts is across the regulator, remaining 110 volts is across the fan, and the fan will be rotating in the medium speed. In the same way is this particular transistor, we can bias this transistor to be half on also. Actually, this is a fundamental fact based on which our whole subject is there now. Complete analog electronic circuits is there based on the way in which we use the transistor in the analog region, in the quiescent region. We set this particular quiescent point, or we sometimes call it as Q point. You might have already studied this in basic electronics. I am revising these facts once again so that you will recall, you will understand in a better fashion. Okay, let me go slightly further. Now for this particular circuit, let us apply KVL at the input side. I can have a KVL. VBB is equivalent to the drop across this resistor is IBRB, and there is a drop across this base to emitter voltage. So we can straight away write that a VBB minus VBE is across this RB. Supply voltage is VBB, across this base to emitter is VBE, remaining is across RB. So we can find out the base current IB is VBB minus VBE divided by RB. This is a straightforward equation. Now similarly for collector current, we can have an expression applying KVL at the output loop. Total voltage applied to this loop is VCC, and there will be a voltage across transistor, that is VCE. This particular point where emitter is connected is called as a ground. Generally ground means zero voltage. Wherever the batteries negatives are connected together, with reference to this particular point, we measure the other voltages. So in general, ground is always with reference to our measurement, it is always at 0 volts. So when this is 0 volts, VCE is from collector to ground. So you can say across the transistor VCE is there. Other side of the resistor VCC is there. So across the resistor it is VCC minus VCE. So collector current can be VCC minus VCE divided by RC. This is also a straightforward equation. I want to tell you one more important point now. Just look at this picture. At the input side, when the voltage is rising, at the output side, voltage is falling. You just observe this. At the input side, voltage is increasing. At the output side, voltage is reducing. Reason is, we connected the switch with respect to ground here now. So at the input side, when the voltage was below 0.5, transistor was off, switch was off. When the switch was off, collector voltage was VCC. When the switch is completely on, collector voltage is 0 ideally. In between, transistor is the active region. So now, when we gradually increase the input voltage, input current increases and base to emitter junction gets forward biased, transistor switches on. When the transistor switches on, voltage which was there in the cutoff region was VCC, voltage in the saturation region is 0 volts, in between it is in the active region. So what happens here is, when the input is rising, output is falling. So in the technical terms, we say output is out of phase with the input. Output is out of phase with input. When output is out of phase with input, we in general say output is 180 degree out of phase with input. This point I will tell again in future also when we discuss amplifiers. Okay, there is a question there in the chat box. Let me address the question. Sir, what point does transistor act as an amplifier? Okay, now we are using transistor in the middle region always in the active region. We set a Q point here. I am going to discuss this later in detail. For now, I will tell only one thing, that we are going to set this quiescent point at VCC by 2. Now I give a small AC voltage at the input. Small AC voltage at the input is going to cause a small change in IB or base current. A small change in IB is going to drive the transistor towards saturation. Let us say there is a negative cycle at the input. That negative small cycle at the input is going to turn the transistor off. Look at this curve once again. Here the difference between cutoff and saturation region at the output is VCC and 0. For example, saturation is 0 volts, cutoff is VCC. Let us say for example VCC is 12 volts, the swing in output is 0 to 12 volts. But correspondingly you see here, the swing at the input is only 0.2 volts. You get that idea? At the input, the change is only 0.2 volts, 0.5 to 0.7, means hardly around 200 millivolts. At the input, it is 200 millivolts swing. At the output, it is 12 volts swing. You can calculate 12 volts divided by 0.2 volts is how much? 12 volts by 0.2 is 120 by 2. 120 by 2 is 60, which means for a small change in input, we are getting a large change in output. This itself is amplification. Amplification means what? A small signal is obtained at the output as a large signal. At the input, it is only 0.2 volts change. At the output, it is 12 volts change. That is what is called as amplification. Otherwise, transistor is simply a switch. We are intelligently biasing it to be used in the active region only. Okay. We will discuss about it more. That is the beauty of the transistor. That is the functionality of the transistor. Let me go to next step. If any other students have any questions, you can put it in the chat box. I will periodically keep seeing that and I will try to answer that. I encourage Sayan that he keeps on asking questions. In future also you keep on asking questions, but other students also should keep on listening to me and keep on asking questions. Yesterday I had told you that you have to follow 4W1H rule. You should keep on asking these 5 questions. What, where, when, why, how. That is the only way to understand science and that is the only way to understand engineering. If at all you have to pursue any other degree like a BA, you need not ask questions there. You are simply studying history or geography that way. But in engineering and in technology, unless you ask questions, you'll not be able to understand. Okay, let me go further. I am going slightly slowly only now because I want you to understand all these basic facts. Later on, we can pick up speed. Yesterday I was in neutral gear, today I am in first gear. Even for the next class also I will be in first gear only. Gradually, when you people are with me and you have understood everything, and when I am convinced that you have understood the basics, then let me gradually increase the speed. Until then, I will go very slowly. Look at this picture now. CE amplification, common emitter amplification. Look at this circuit. This is called common emitter circuit. Why? Emitter is connected commonly to input and output. We are giving input at the base. We are taking output at the collector. Emitter is common. So emitter is common means emitter will be at 0 volts. With reference to emitter only, we measure the input voltage and output voltage, or input current and output current. So this is called common emitter amplifier. So remember one thing, in case of a common emitter amplifier, always the output will be 1. Yeah, if I am not audible, wait for some time. Because of this network connection issues, you will have these hearing issues, you will have to bear with it. Anyhow, I am going to record this, I am going to put it in the Google class. If at all you have disturbance during this lecture hour, you can always go back to the Google class and watch the recording. Okay, until then you please bear with this network connection. I hope by October, if things get resolved, we can always have a one-to-one interaction in our department. Until then, we will have to bear with the situation. Let me come back to common emitter amplification. I gave the same example here now. Let us say to this transistor, we connect only 0.6 volts. This is a hypothetical example. Okay, this I have written only for the sake of understanding. Let us say we give only 0.6 volts. Now recall this particular curve. At 0.6 volts, transistor is half on. Recall that way. Now, purposefully we are giving 0.6 volts so that transistor is half on. That is the method of setting the quiescent point or Q point. Now, I set this half on by giving 0.6 volts. Then imagine I am connecting one AC source in series with the power supply. This AC source I am giving only 0.1 volts peak. That means 0.2 volts peak to peak. Look at this picture here. Initially DC voltage is 0.6. Later on, after some time, I am switching a AC signal which is 0.2 volts peak to peak, 0.1 volts up, 0.1 volts down. Now at the output side it is the same. It is the collector resistor and there is a supply voltage. Just a minute. There is a call here. I am just pausing for some time. Hello students, I am resuming back. That one time exit schemes exam is going on. So some official signature was required. That is why I paused here now. So let me continue. Let us say we set this 0.6 volts for the transistor to be in the quiescent point. Then we apply this AC signal. Now look at this picture. When I apply 0.6 volts DC, transistor is exactly at VCC by 2. You can see this. The transistor is exactly at VCC by 2. That means transistor is half on now. Now we apply a small AC signal, 0.1 volt up. Now you can see here, when the transistor's base current is increasing, it is turning on. Transistor is turning on. When it is turning on, it is going down to 0 volts. Similarly, in the negative cycle, from 0.6 volt it is coming down to 0.5. Now, because of the negative voltage, base current at the transistor is reducing, and if it is below 0.5, transistor is turning off. So you can see, when the input signal is rising, output signal is falling, and when the input signal is falling, output signal is rising, which means there is a 180-degree phase shift when compared to the input. So even in the case of a digital circuit, if I am using the same thing as a switch in the digital circuit, when the input is 1, output is 0. When the input is 0, output is 1. That way, this itself can be one inverter circuit. If AC is not given, let us say when only DC signal is given, this is working like an inverter. So common emitter amplifier is always in the digital mode, it is like an inverter. In the analog mode, it is like a 180-degree phase shift amplifier. Now look at the swing. Output you have 0 to VCC swing, input you have only 0.2 volt swing. As I told you earlier, if supply voltage is 12 volts and if input is only 0.2 volts, it is 12 by 0.2 is 120 by 2, 60 times is the gain for an input signal. This is the specialty of common emitter circuit, which is working like an amplifier. So CE configuration is an inverting amplifier. Now I can tell you the gain here. Voltage gain AV is VCC minus 0. Maximum is VCC. Minimum is 0. VCC minus 0 divided by this input voltage is 0.2. That is the gain. And current gain is IC by IB. That is beta itself. Because base current is much smaller in microampere. Collector current is in milliampere. There will be in general 1000, 2000 times gain there. That is dependent on the beta here. Beta is given by the manufacturer himself. So that way, the circuit is going to give you voltage gain also, current gain also. That is how the circuit is working like a amplifier. Now, I want to tell you one more point here. There is a phase shift. What happens if this voltage increases above 0.7 or if this voltage reduces below 0.5? What happens? If this voltage rises above 0.7, here the output cannot go below 0. Similarly, if the input is below 0.5, output cannot go above VCC. So what happens there is a clipping happening there. The sine wave, maybe at the input it is sine wave only, which is larger than 0.2 volts peak to peak. But the output, you will not get a sine wave. You will get a clipped sine wave. The peak will be clipped. Even the valley will be clipped. That means, if Lata Mangeshkar is speaking at the input, Lata Mangeshkar is singing at the output, you will hear Usha Uttup's music. Why? Because signal gets distorted if there is excessive input voltage. That is where we have to take care. Amplifier designers have to take care that always amplification should be faithful. The meaning of faithful amplification is output waveform is retained as the input waveform. If the output waveform's shape changes, then it is an unfaithful amplification. That is why design of an amplifier is always a critical thing. Where even a digital circuitry can be automated. Analog circuitry cannot be automated so easily. For a digital circuitry in a C language, program can be written, but for an analog circuitry, it is not so easy to write a program in C language. So that way, our aim in this particular course, in this semester, is how do we design amplifiers? That is our goal initially. Then gradually, how do we use amplifiers as oscillators? That we are going to discuss in the modules in future. So first thing is, this is a hypothetical circuit diagram which I have shown you. But actually, we cannot have a circuit like this. We cannot have a 0.6 volts power supply. We cannot have 0.1 volt peak signal, because the signal is always a naturally occurring signal. For example, my voice, I cannot say that my voice has to be only 0.1 volt peak. It is varying. Similarly, supply voltage also, I cannot say it is 0.6 volts. Now, how do we take care of these things when we design amplifiers? We are going to discuss in the future classes. Until then, you please understand all these basics thoroughly. Now, there are some conclusions. For a biased transistor, a small variation at the input results in a large variation at the output because of the biasing due to switching. Transistor is a wonderful switch which can work in 3 regions. What is the meaning of biasing? Biasing is the application of proper voltages to the circuit so as to set the quiescent point. I told you about the word quiescent, quiet as well as sensitive. That is called quiescent point. You have to pronounce it this way only. You have to pronounce this word as quiescent point only. You should not mispronounce this. And voltage gain occurs due to the switching of the supply voltage by the transistor. Actually, transistor is not doing any gain. Transistor is giving a current gain. We are giving a voltage gain. For example, if your the supply voltage is 12, then the gain is 120 times. Sorry, 60 times. If the supply voltage is 24 volts, if the supply voltage itself is 24 volts, 24 divided by 0.2, then the gain is 120 times. So, choosing the power supply, we will get a voltage amplification. Current amplification is the property of the transistor itself. Voltage gain is occurred because of our design. So, voltage gain occurs due to the switching of the supply voltage, whereas current gain occurs due to the construction of the BJT with the base region smaller, collector region larger. That is where in some textbooks there is an error where they show all the 3 regions in equal area. But actually it is not so. Actually, collector is much larger, emitter is medium size, base is really very small. That is why base can handle only a very minute current in microampere. Then only transistor switches this way. If all the 3 regions are equal, then the transistor will not work in this manner. When the BJT is biased such that VC equals VCC by 2, the circuit can be utilized as an amplifier as an analog circuit. Instead, if a pulse is provided at the input, then the circuit works as a NOT gate as a digital circuit. In other words, if the BJT is kept in active region, then it is an analog circuit. If the BJT utilized in between cutoff and saturation, then it is a digital circuit, as I have told you already. So, BJT fully off is cutoff, BJT fully on is saturation, BJT partially on is active. These are the output characteristics. This I will discuss in my next class in detail, because already WebEx is showing me the time limit. See you in the next class in the afternoon. In the afternoon at 1:50 I have one more class, and I will see you there. Until then, take care and bye-bye. Okay, still 5 minutes is there. WebEx is telling me I still have 5 minutes. So fine, let me complete this. Just a minute, I will sip a little bit of water. After this class is over, in the Google class, I am going to post the link for the attendance. I am not going to send you the Google link in the WhatsApp. Please check the Google class itself. There I will be giving you the link for attendance. There only you mark your attendance. That will be our practice for future classes, because it is easy for me and easy for you. Everything will be available in Google class there. Now look at this picture. This is output characteristics which is generally present in the textbooks.